what we'll carry on to do here today is the calculations. Okay? So you will first learn how to do calculations involving weak acids and bases. You need to take into consideration the partial dissociation. Okay, the fact that dissociation involves in an equilibrium. Okay, you need to use the Ka or Kb to find the H plus or the OH minus concentration at equilibrium. Okay, so calculating the pH, you know that the pH is a negative log of the H plus. Now, for a strong acid, this is very straightforward. Okay, there's 100% dissociation. So the concentration of the acid Ha is the same as the concentration of the H plus. And this is one way to check whether it is a strong acid or not. Okay, so likewise for a strong base, the same case applies, or similar case applies. For weak acid, there is partial dissociation. Okay, the concentration of the weak acid, the initial concentration of weak acid is not equal to that of the H plus. Okay, so you need to calculate the H plus using the Ka, and likewise it is the same case for the weak base. Alright? Okay, so write the expression for Ka for ethanoic acid. Okay, so write the Ka according to the equation or equilibrium that you are given. Okay? If you are not given an equation, then you write one down and then write your Ka expression according to the equation that you write. So in this case, that is the expression. Now, if you had written down the equilibrium, okay, using water, that's fine. But the Ka expression, okay, you exclude the water. Alright, and then you can just write H3O plus. Okay, you exclude water because it will be part of the definition for Ka. Okay, so calculate the pH of 0.15 mole per dm cube ethanoic acid. They give you the Ka. Okay, so that's your the equation. Now, write out the ICE table, the initial concentration, the change, and the equilibrium. Okay, so you will be able to get that expression. You will realize that the concentration of the CH3CO minus and the concentration of the H plus are equal because both of them came from the ethanoic acid, and when it dissociates, it is in a 1:1 ratio. So they will have an equal concentration. Okay? So that is the expression. Okay, so for ionic equilibria, you can make an assumption that the X is very small. I stress this for ionic equilibria. You cannot do this for normal chemical equilibria. Okay? Because in this case, we know that the value of X is much smaller than the initial value. Okay, so you can make that assumption, and therefore the Ka expression simplifies to this. Okay, and then you can solve it, and you get H plus, okay, which is equal to X is 1.64 times 10 to the power minus 3. So if you look at this, is it a valid assumption that X is much smaller? Yes, because it's 100 times smaller. Okay, 2 orders of magnitude smaller. So it's fine. Alright? Okay, then you take the pH and it will be negative log of 1.64 times 10 to the power minus 3, so it's 2.78. Okay? Okay, so let's look at example 1.8. Okay, So here they give you the pH. Okay, this is at equilibrium already, and at 25 degrees Celsius, calculate the Ka. So from the pH, you calculate the H plus concentration. Alright? So because this is, they don't say that it's an initial. Okay, they tell you that they present you with this solution and they tell you the pH is that. So they are implying that it is at equilibrium. Okay, so the initial zero, so you assume that initially it is 0.0495, okay, for the acid, the HA. Okay, so for the CH3, CH2CO minus, the anion, it will be 0, the H plus will be 0. Okay, so we are assuming at before any dissociation has taken place. Okay, then at equilibrium, you would have calculated from the previous step that the H plus is 8.91 times 10 to the power minus 4. Okay? Therefore, the change, the concentration of the acid, okay, would drop by 8.91 times 10 to the power minus 4, so minus 8.91. The anion will be plus 8.91 times 10 to the power minus 4. Okay? So this will be your equilibrium values. Okay? So equilibrium expression will be there. Okay, substitute the values in, and then you can get the final value. Done? Okay. Now, just to recap. So, if you have acid, it will be a proton donor. Okay, that's what we call acid. In this case, the water is the proton acceptor, so it's the base. Alright, and then you get the conjugate acid, is the HCO plus, and then the conjugate base, which is the RCOO minus. Okay? So Ka expression, and that is the simplified Ka. Okay, so the other point I want to reinforce, whichever equation you write, do not include, for Ka, do not include the concentration of water, because it is defined without using the concentration of water in the expression. Okay? I'm stressing this because this is a matter of principle. Okay, you need to understand this. Okay, so base dissociation. The base is a proton acceptor. Okay. Then you have a proton donor, in this case water. And then you have the conjugate acid. And OH minus is a conjugate base of water. Okay? So, Kb expressions and units are mole per DR cube. Okay, so let's look at example 1.9. Write an expressions for Kb for ammonia. At the moment, I'm considering whether I should tell you the formula for ammonia. I suspect some of you don't know, but it will be a deep shock to my system if you don't know. Nicholas Go, so what have you done with the Croatian flag? Hong sir, were you a Croatian fan? Yes, that's why you got a fever, is it? Okay.
Use these. This is right. Go on, that's saline for 5H6, ammonia is acid. Oh, she wants to show up.
That might prove helpful for some of you. So, that's what you should get.
It's the right here. Okay, you know the motor.
Okay, so Kb expression.
Oh, must be
Okay.
good.
Okay, continue doing if you have finished, you can do example 1.10. For those who are stuck, after this, the next step is to draw the ICE table. So draw that, then fill in whichever things you. It will be similar to the previous example.
They must use ammonia is
Okay. See, can you get this? Initial. Okay. You don't know what the change is, right? So you put X. So the ammonia should decrease, the ammonium should increase, the OH minus should increase. For the water, you just put, you can just, don't have to write anything, or you want, you can put a dash. Okay? They won't expect you to write anything. So at equilibrium, this will be the value. Okay? And then you substitute, write the expression, then you substitute into there. Okay? You can make the assumption that X is very small. So 0.125 minus X is actually just 0.125. Okay? And okay, can I move on? Any objections? Okay. So concentration of OH minus is 1.49 times 10 to the minus 3 mole per dm cube. BOH will be 2.83. pH is 14 minus 2.83 is 11.2. Okay? Okay? You need to find the value of X, right, Nelson? Concentration of OH. So you are asking, why do I need to simplify, or? Okay, people hang on. I want to try to understand what Nelson is asking me. Okay? This one, right? So why do I need to write this? This KB equals to this. This one. Why can't you just write this? If you can see that the KB is this, you can just jump straight to here. You, okay, Mr. Tan will help you. Okay. Now, write an equation for the ionization of ethyl amine, CH3, CH2, NH2. So this is an organic compound with a group that functions like ammonia. Okay, it's similar to ammonia. Alright? So, the R represents an ethyl group, which is the CH3, CH2 group. Okay? So, when you have water, okay, you will form a dative bond with the H, just like in ammonia, and then you can get that equilibrium. Okay? So it's exactly the same as ammonia, except instead of one hydrogen, it is replaced by a CH3, CH2 group, which is an ethyl group. Okay? Then you are left with ethyl amine. And okay, those of you who are ready, you can go and start on part B. Calculate the degree of ionization.
Count. What you do?
Right? Okay, so you have the equilibrium, you have the initial, okay?
No.
Now, in this case, right, you are given the pH. So you calculate pOH, then you calculate the OH minus concentration. Okay, then you get that. Okay? So, if you remember alpha, which is the degree of ionization, it is the amount of dissociated over the total. Okay? So it will be that value. Can? Done?
Your job.
Okay.
Down there.
Are we done? Okay, I would be more sympathetic if the people who say they are not done are not spending their time talking or copying. And I can be extremely unsympathetic if you irritate me enough. Okay? By the way, my class should know that I am observing them very carefully. Don't point fingers, just okay? Okay. Now, which is a better indicator of acid-base strength, pH, alpha, or Ka. Okay. Now, if you look at this, you guys need to train yourself in this. For a key skill in science, if we give you numbers, we give you a table, I expect you to look at it and make sense of it. Okay, so Nicholas Wong, you have triggered my interest to the point that you get to answer this question. What do you notice about this table? Tell me. You look at the table, you should be able to tell me. After Nicholas Wong, there will be a number 2. If Nicholas Wong doesn't answer. Now Nicholas Wong is trying to calculate what are the risks of me just shutting up and nothing happening to me. 0. Hurry up. Tell me the trend for pH. Decreasing with? The pH decreases with, increases with concentration. Increases with concentration, right? Alpha? In the alpha increases with, okay, with decreasing concentration. Ka does not vary. So for science, if you want to compare this, we are talking about the same acid. Okay, you don't want the basis for your comparison to change depending on what the concentration is. So the best thing is to actually just use the Ka. Okay. Now the other thing, however, Ka, you must remember to keep the temperature constant. If not, it will vary also. Okay, so at the same temperature, Ka of a stronger acid is higher than that of a Ka of a weaker acid, regardless of the concentration of the acid. Please note that this applies for weak acids. For a strong acid, they will never quote you a Ka, because if you go, at least at A levels, because if you go and look at the values, K for strong acid is supposed to be 100% dissociated. So the K expression will require you to divide by 0, which K is undefined. Okay? Okay, so
divide by the initial thing. That's what I remember. Yeah, should be.
Now, pH, okay, you must be aware of the concentration. Okay, so just by looking at the pH here, you may think that ethanoic acid is a stronger acid than HCl. But that's not true, it's just because the HCl concentration is very low. Okay? So alpha is dependent on the concentration of acid, increases with decreasing concentration. So look at page 4 there. And okay, so now we are going to look at the next thing is salt hydrolysis. Okay? Now, couple of things I want you to